Okay, now we're going to work on SN1. That's unimolecular nucleophilic substitution. And we got this, which is going to be our generic formula. Now, the notation I'm going to do here is the factors that you need in order for SN1 to happen. So I'm going to write factors. And we need, first of all, a nucleophile, obviously. I'm going to say nucleophile like that. And in this case is our OH. So right now it's OH minus. Pretty much this is a base. So if you want, I can write here base. We need a substrate, which will be this molecule right here. So the molecule being worked on, substrate. And I will write C3. We have 1, 2, 3. So I will say 3, C, Br. That Br there. And that would be our substrate or the molecule working on. And lastly, we need a leaving group. The leaving group, you will see it commonly like that, and that is our Br. Actually here, it shouldn't be. You get the Br down here as a leaving group. Why is the leaving group? Because that's the group that takes the electrons and leave. So, we check, we do have a nucleophile, we have our substrate right here, and we have a leaving group. What you gotta remember is that the nucleophile has to be a better base than the leaving group in order for SN1 to happen. If it was the other way around, if we had the OH here and the Br minus as a nucleophile, then you would not get any net reaction. So let's see what happens here. You have this molecule plus a nucleophile, you end up with that molecule and your leaving group there. So how did this happen? SN1, what I need you to remember about SN1 is that it is a carbocation intermediate. That will have a lot of implications, but we'll get there. So, this one leaves, meaning it takes the electrons from the bond, and you will get it here, plus Br minus. So this one leaves, and then you form a carbocation right here. And now I want you to think of the hybridization of it and the geometrical arrangement of that molecule. So once you get your carbocation, the nucleophile, the best nucleophile, in this case the better base, which is OH, is going to attack the carbocation. Now, the carbocation has sp2 hybridization, so it gives you a trigonal planar arrangement. That means that it is flat. So the nucleophile can either attack it from the top or it can attack it from the bottom. And that will make a difference when it comes to stereochemistry. So you will get 50% of the OH that attacked it from the top and 50% of OH that attacked it from the bottom. But that's pretty much SN1. You gotta remember it is a carbocation intermediate, so there might be rearrangement. When you have it here, it's a tertiary carbocation, so that's pretty much as stable as you'll get in that molecule, and that's that. Okay, let's see an example of this. So we have our substrate. We have a good leaving group. Halogens are good leaving groups. We have our nucleophile ready to go. And then we see two products. So let's see how we arrived at that. I'm going to make the mechanism. So I will copy this. C, CH2, CH3. Then I have an H in the back. Br. And then a CH3 to the side. Plus OH minus my nucleophile. So I know what's going to happen. This bond is going to break. The Br is going to take the electrons and leave. So what I'm going to get is C, CH2, CH3. And then what I will get is the H right here. And my CH3 here. Now, what I want you to picture is this carbon in 3 dimensions. The carbon is standing like this. It is trigonal planar, so it is in one plane. You have your ethyl group on the top. You got going to the back a hydrogen, and then coming towards you, you have a CH3. So the nucleophile Br minus, because it took the electrons from the bond. So the nucleophile here, on this step, let me rewrite it. The H in the back, and then coming towards you, we have the CH3, the methyl. So the nucleophile right here can either attack it from this side, the carbon, or other molecules may attack it from this side. So that's why you will get a 50% of those two, because you have the same amount of chance to attack it from this side than to this side. So I will make this one right there, and I will say that I have my carbon here, CH2, CH3, then I have my H going to the back, I have 1 with the CH3 right here, and coming to you, you have your new bond with the OH. And the other molecule, that is, if it was attacked from this side, you get the OH on this side. Now, if you attack it from this side, you will have your carbon here, CH2, CH3. You got your H in the back. And then on this side, you have your OH. And then your CH3 to that side. So, it's important, the stereochemistry here, because this is a chiral carbon. You have 4 different groups attached to it. You have OH, CH3, an ethyl here, and a hydrogen. So, since it is a chiral carbon, then it does matter the stereochemistry. Now, if you think of this, then you can say, okay, my main group is this one, so we're going to take this one as 1. Then you say this one's the second one, so I say 2, and then this one 3, based on the weight of the group. So since it's going this way, like a clockwise, then it's going to be R. This one, I'm going to say this is 1, I'm going to say this is 2, and this one is 3. So it's going counterclockwise, so it's going to be S. And that's it. Okay, another example. We're still in SN1. So, we have our substrate, we have the nucleophile, and then we have our leaving group, good leaving group, and we have our molecule right there. So let's see how that happens. I'm going to copy this. CH3, CH, CH3, CH, Cl, CH3, plus my nucleophile. So, SN1, we said it's carbocation intermediate. What happens is that the leaving group leaves first, and it takes the electrons with it. So we expect it to get here, CH3, C, CH3. This one has an H, CH, CH3, and your carbocation is right here, empty orbital. Empty orbital because there's no more electron pair right there, so you do have an empty orbital. Now, what's going to happen is we do have a secondary carbocation. Let me write it here. CH3, C. I'm going to draw my H. This H, I'm going to put it down. CH3, then CH, my carbocation right there, and CH3. So, what's going to happen is we have a secondary carbocation, but right next to it we have the potential of a tertiary carbocation. So what's going to happen is we have a 1,2 hydride shift. So the hydride is going to move with the electrons. We have to remember that hydride has 2 electrons. That's a hydride. Hydrogen, and this is minus. Hydrogen has 1 electron and 1 proton, so the overall charge is 0. And we have a proton, which it doesn't have any electrons, it only has 1 proton, so the charge is plus. So what happens here is a hydride shift, so it leaves with the 2 electrons of the bond to get into the empty orbital, but now we have this carbon right here with an empty orbital. So what's going to happen is we have CH3, C, the empty orbital right here, CH3 up here, CH. Now this carbon is going to have 2 hydrogens now because of the hydrogen shift. So CH2 and CH3. This still plus OH, or nucleophile. It has not moved yet. So we are going to copy that in here. CH3, C, CH3, plus CH2, CH3, plus our nucleophile. So we know that the nucleophile is going to attack the positive center of the carbon, and we're going to get CH3, C, CH3, CH2, CH3, and OH down here. I'm not showing the stereochemistry because this is not a chiral carbon. You have 2 groups that are the same, so there's no possibility of being a chiral center. And that's your mechanism.